Bohr's atomic model required a proof beyond the atomic spectra. It needed evidence that electrons can transition between energy states by absorbing or emitting precise amounts of energy. In 1914, James Franck and Gustav Hertz attempted to explain fluorescence through elastic and inelastic collisions between electrons and atoms. They developed a vacuum tube with 3 electrodes, a negative cathode, a positive anode, and a grid. The external electrical circuit consists of a switch S, a battery V1, and a potentiometer that allows the voltage on the tube to be continuously adjusted. Furthermore, the V2 battery is included to maintain a constant potential difference between the grid and the anode. The anode's somewhat lower voltage than the grid prevents electrons with insufficient energy from reaching it. Ammeter A displays the intensity of the electric current in the outside circuit. A distinct electric circuit, not illustrated, heats the cathode, resulting in the formation of a cloud of electrons surrounded by thermoelectronic emission. After activating the switch, the external electrical circuit is closed and the electrons collectively drift towards a positive grid. The charged electrons are accelerated in the electric field. They gain energy in proportion to the voltage between the cathode and the grid. This energy is most elegantly represented in terms of electron volts, the charge of the particle multiplied by the voltage between its starting and ending positions. However, because the initial voltage is close to zero, the electrons do not have enough energy to pass through the grid. The ammeter detects no electric current. By increasing the voltage on the tube, the grid's potential relative to the cathode increases, causing the electrons to gain additional energy. As a result, the number of electrons that make it to the anode increases. The current in the tube rises constantly until it reaches a maximum value known as the saturation current. At that voltage, all electrons generated by thermoelectronic emission reach the anode. Up to that point, the change in the electric current in the tube completely follows Ohm's law. If the resistivity remains constant, the electric current will steadily grow as the voltage increases. This is not the Frank-Hertz experiment. This is the way a conventional electrical vacuum tube behaves, a tube with no molecules in it. But what happens if mercury molecules are introduced into the tube and the entire process is repeated? As the voltage in the tube increases, the electric current starts to rise. However, at a certain point, it suddenly drops before continuing its ascent. This pattern was repeated multiple times. The graph of changing electric current in a tube with mercury vapor is no longer linear. It has a sawtooth-like shape. Franck and Hertz discovered that these sudden drops in electric current always occur at precisely defined voltage values. The gap between these voltage values remains constant, 4.9 volts. Furthermore, at voltages where the current drops, UV light with a wavelength of 254 nanometers is emitted. The presence of mercury in the tube caused a change in the behavior of the electrons that comprise the electric current. For whatever reason, continuously accelerated electrons in a tube with mercury vapor suddenly lose energy when they reach 4.9 electron volts. Franck and Hertz were unable to adequately explain the experiment, but they reported the findings. As soon as Niels Bohr saw the experiment's outcomes, he knew that his own atomic model had been validated because the evidence presented did not rely on atomic spectra. Bohr described the energy of 4.9 electron volts in terms of the first excited states of Mercury atoms. It is the energy that propels the electron to higher energy state. Mercury atoms cannot utilize thermal electrons with energy less than 4.9 electron volts. It is insufficient to elevate the Mercury electrons to a higher energy level. The collisions between accelerated electrons and Mercury atoms are completely elastic, with no energy transfer taking place. However, when an accelerated electron reaches 4.9 electron volts and collides with a Mercury atom, the Mercury atom absorbs its energy, as this is the energy needed to raise the Mercury electron to a higher energy state. This electron will soon transition back to a lower energy state and emit a photon carrying the same energy of 4.9 electron volts with it. When the wavelength of the emitted photon is calculated, the result is 254 nanometers. This value matches exactly what Frank-Hertz observed. The Bohr model of the atom has received crucial confirmation.